हमारे साथ जुड़े हुए हैं डॉक्टर मनिंदर सिंह जी, और उनके बायो के बारे में आपको बता दूं दोस्तों. सर इज ए मटेरियल साइंटिस्ट एंड ही हैज कंप्लीटेड हिज PhD इन द मटेरियल साइंसेज एंड from JAIST in 2019. His studies on sustainable nanostructure thermoelectrical materials were published in a number of journals. He is currently creating sensors in his capacity as lead scientist in a technology-based company. He conducted extensive research on the advanced composite materials postdoc, working with the polymers, hydrogels, and the nanomaterials, among other materials. With over 8 years of experience in the polymeric and the nanomaterials, Maninder sir brings in a wealth of knowledge to his research, aiming to address global challenges. And now sir is with you and will guide you towards this research field. And with us Dr. 𝗲𝗲𝗲𝗹 is also present. आपने उनको देखा भी हमारे पहले सेशंस में. सर इज एन असिस्टेंट प्रोफेसर इन SRM यूनिवर्सिटी. और वेरी फर्स्ट ऑफ ऑल आई वुड लाइक टू थैंक SRM यूनिवर्सिटी दिल्ली NCR campus IST, which is in Ghaziabad, and which has provided this facility in the collaboration of Chem Academy for this career development sessions. Okay, let's start session. Sir, please, Maninder sir, बच्चों को guide करिए sir, please. बच्चे
Thank you very much. Thank you, Pradeep and Dr. Ravi, for having me on this platform. And I'm feeling really happy to share my research experience and my life experience with the students and the people who are joining at this platform. So today we'll begin with the topic of nanotechnology and polymer chemistry for sustainable ecosystems. So I'll give my brief introduction. Currently, I'm a chief material scientist with German-based tech-based company where I am creating biosensors, or you can say the electrical sensors for the automotives and the aviation industries. But my journey was not so easy, so I'll take you through my life journey. So from where I began, I take you there to my institute where I started doing my PhD research. I did my master's actually in India from Delhi University, chemistry department. And then from there, I started, I went to Japan where I did my PhD. And as you can see on the slide, the institute name is Japan Advanced Institute of Science and Technology. It's on the east of Japan side. You can see here, and you can see that there are different kind of seasons. You can see this is the main building of JAIST. Dr. Ravi can remember very well. And then we have summer season and the cherry blossom season. In Japan, you can find a beautiful cherry blossom season because different kind of flowers you can see in that time. And the autumn season, then you can see heavy snow in the months of December to February. It's really beautiful. I mean, you can enjoy each and every season there. So before going further into the research area, I want to show you something about JAIST where you can learn from how can you start your research work from there. Okay, just a moment.
Unique culture, delicious food, quaint scenery. Japan is visited by some 20 million tourists a year and is one of the most popular countries in Asia. Why not spend your graduate school days in a country as fascinating as Japan? Japan Advanced Institute of Science and Technology, JAIST, is a national university located in Ishikawa, a prefecture with a full range of high-quality tourism resources, including the natural environment itself, as well as historical heritage, traditional crafts, a delightful culinary culture, and soothing hot springs. The prefecture also has an excellent medical environment and leisure facilities. The prefectural capital, Kanazawa, also known as Little Kyoto, is one of Japan's leading tourist destinations. It is the Hokuriku region's most lively city because it is a popular place for shopping with gourmet cuisine. With the opening of the Hokuriku Shinkansen in March 2015, the trip between Kanazawa and Tokyo is now a mere 2.5 hours. JAIST was founded in October 1990 as the first national independent graduate university in the country. The institute focuses on only graduate education being a center for world-class research in advanced science and technology, and thus the institute has no undergraduate courses. At Monosono Lab, we carry out cutting-edge research on nanoparticles. Our aim is to develop novel applications for nanomaterials in the biomedical, environment, and energy fields. We strive each day to create state-of-the-art nanoparticles. Monosono Lab has 5 distinguishing features. 1. Interdisciplinary research. The application of nanoparticles covers various fields, from biomedical to environment and energy. Engaging in interdisciplinary research covering a range of fields encourages a broad knowledge base. 2. Nanoparticles in a variety of materials. We produce nanoparticles in a wide variety of materials, including metals, semiconductors, and magnetic materials. Through the precise control of size, shape, and composition, and by also functionalizing their surfaces, we're able to create tailor-made nanoparticles. 3. Comprehensive joint research. In order to carry out interdisciplinary research aiming at a wide range of applications, we actively conduct joint research with researchers from various groups, both in Japan and internationally, whether in industry, academia, or government. 4. A rich international atmosphere. Our laboratory accepts students from all over the world. In recent years, international students have exceeded 50% of our student numbers. And as a natural outcome, broken English has become our official language. 5. Work-life balance. At Monosono Lab, we recommend real-life experiences of Japanese-style living. These include playing sports, singing karaoke, or going on trips together with other members of the lab. There are also opportunities to do homestays with local families during the summer or winter holidays. State-of-the-art science studied in Japan, and a rich grad school life. Excitement and fun await you each day. We welcome you to enjoy a wonderful student life at Monosono Lab. Please feel free to contact us.
Hope you had a good look at the life in Japan and the university there. I spent almost 11 years there, and then where I did my PhD for 6 years, then learning most of the instruments. JAIST provides all the in-hand experience of all the instruments that you require for your research. I mean, in India, in most of the universities in India, you have assistant or some trainee or some kind of intern to help you, but in Japan you can use almost all instruments by yourself, so you have in-hand experience with all the instruments. So yeah, you can manage the instrument. I mean, if it's broken, you have to manage the instrument by yourself, so it gives you wide experience with the instruments as well. So okay, let me share my slides. Okay, so you're familiar with JAIST and a little bit of Japan. So I'll take you through the research work that I did during my PhD. So I started working in Monosono Lab, which deals with nanoparticles, where I worked on thermoelectric materials in which semiconductor nanoparticles were used. And I was also directly or indirectly connected with creating nanoparticle for biosensing and biofunctionalization, as you can see. For nanoparticles for magnetic hyperthermia, there are many applications you can use by synthesizing different kind of nanoparticles. So I'll give my brief introduction of my PhD research work. I used nanoparticles in creating sustainable thermoelectric materials. So I'll begin with short introduction of what are thermoelectrics. So as you know that factories and the nuclear power plants and automobile release waste amount of heat. How can we utilize that heat? So that heat can be utilized by converting them into electrical energy. So then the most of the waste energy is under 400 degrees Celsius, and this much of heat is, this much of heat, 400 degrees Celsius, enough to create an electrical energy. So we created a device which can convert the waste heat to electrical energy using a thermoelectric device, as you can see here. So this thermoelectric device works by conduction of electron flow from the heat source to the cold side. So it creates a potential difference across. So and the good part of this thermoelectric materials are they have no moving parts, so there is no noise and the lightweight. Basically, what we have to do, we have to increase the thermoelectric coefficient so that we can enhance the efficiency of the thermoelectric device. So what are the current thermoelectric materials? The current thermoelectric materials were formed by bismuth, antimony telluride, a lead telluride, and lead sulfide, and they had this high ZT value. But the problem was we have to create, but the thing is we have to create the sustainable thermoelectric material. So the problem with the existing thermoelectric material was the telluride which was using in the previous thermoelectric material, it is less abundant. Telluride was less abundant, and the toxicity of lead and telluride was also high. And telluride is expensive as well. So that's why we need to create some material which can be utilized for sustainable, which can be used for sustainable ecosystem. So we can consider them as not sustainable materials. So what we have to do, we need to look for alternative thermoelectric materials. So first condition has to be abundance. Okay, so as you can see, telluride, low abundance. So that's why we choose copper and sulfur, which has high abundance, and the toxicity levels of copper and sulfur is less than the telluride and the lead. And even the expensive sulfur is less expensive, sulfur and copper are less expensive than telluride. So these are the advantages over the existing thermoelectric material. So we choose copper and sulfur over the bismuth telluride elements. So before going deeper into the nanoparticle form, thermoelectric nanoparticles, so I want to discuss something, what are the nanoparticles and how it is formed. Nanoparticles are in the range of 10⁻⁹ meter, right? So how nanoparticles are formed? One is top-down approach, where you can see you destroy the bulk material which is in micrometer size into the nanometer, and other synthetic technique is where you create from atoms, you create a bigger particle. I mean, you go from 10⁻⁻12 to 10⁻⁻, from angstrom level to 10⁻⁹ meter level, where you can create the nanostructures. And the mechanism behind is that in this figure you can see that there is a correlation between time and the nanoparticle formation. Initially, when you put a metal salt, you can see the gold 3+ and gold 3+. When you put in the solution and it grows with time, you can see the metal salt reduces and it forms the metal gold metal. And then when further the time increases, the particle grows and it forms into a nanoparticle. So you're now familiarized with the formation of nanoparticles. So I'll discuss my research work, what I did in my PhD. So I created copper and sulfur nanoparticles, where I use copper nitrate and iron sulfate precursors, salts, and I mix them together to create copper sulfide and iron sulfide nanoparticles. As you can see, these are the TM images. I'm not sure whether you're familiar with the TM instrument, where you can see the nano-sized materials. So I created copper iron sulfide nanoparticles in different ratios. So so I created 5 samples, which is composed of pure copper sulfide particles, mixture of copper and iron sulfide nanoparticles. So you can see the images, a spike formation. So these are kind of nano flowers you can see. So nanoparticles cannot, it cannot be sphere, it can be of any shape, and it has the shape dependent properties. So we have to remember and keep in mind that the with changing shape of the nanoparticle, the end property will change. So then there are certain and to identify and to characterize if our nanoparticles are the same what we want to create. So what we did the XRD. So XRD is an X-ray diffraction where you can see that each the nanoparticle that you have created have the characteristic peak, the Bragg diffractions you can see here, and with all the XRD pattern we can confirm that where we have the desired end product, that what we wanted to create. And these are the TM and certain high-end instrumentation where you can identify sulfur, if there is sulfur, if there is iron, if there is copper. Okay, and the overlay of all these images can tell you that copper and sulfur, iron and sulfur are there in particular ratio. And in the second part, what I did, that I created copper sulfide nanoparticles separately and iron sulfide nanoparticles separately, and I mixed them in different ratios. I created almost 5 samples, and you can see a very good spherical particles here. But when I inserted iron into it, you can see the particle size changes. So inclusion of different kind of element can change the shape and size of the nanoparticles. So this is very important. So before studying any nanoparticle and their properties, you should learn that the nanoparticle that are formed has certain effect on the end product and the properties related to it. So, and the research work that I was doing, I was trying to increase the thermoelectric efficiency of the material, and I succeeded. So basically this chart is the ZT value. Basically this chart helps us to understand that whether we succeeded in increasing the thermoelectric efficiency. So this pink line tells us that this nanoparticle solution, copper iron sulfide nanoparticles, we achieved a good thermoelectric efficiency all over. And if we compare with the literature work, and it's much more than the. So here is, let me show you the. So what we do, we create nanoparticles and we try to compare that with the bulk material. The thermoelectric efficiency that we got is 0.55, and that is much more than the existing literature value. So we succeeded in our research work. So basically in PhD, what you do, that you have to create an upper edge over the existing research.